Software architecture styles, also known as architectural patterns, define the structures and methodologies for organizing software systems. Each style has unique characteristics and suits different types of projects and organizational goals. Hi, I'm Vivin Arana, and I'm going to go over different or some of the major software architecture styles in this particular video series. So first we are going to look at layered or entire architecture. Now this divides the system into layers with specific roles and responsibilities. Common layers include presentation, business logic, data access, and data storage. Changes in one layer usually do not affect others, promoting separation of concerns. Next, we'll look at event-driven architecture. This centers around the production, detection, consumption of, and reaction to events. This architecture is highly adaptable and is suitable for environments where actions are triggered by external events. Next, we'll look at microservices architecture. Structures an application has a collection of loosely coupled services, each implementing business capabilities. This architecture enables independent deployment of service components, which is beneficial for agile development and scalability. Next, monolithic architecture builds the entire application as a single and indivisible unit. Typically, all components are interlinked and interdependent, simplifying deployment but complicating scalability and understanding. Next, we're going to go in details of service-oriented architecture, SOA. Now, this composes applications by assembling distributed and reusable components of service or services which communicate over a network. SOA emphasizes interoperability and modularity, making it ideal for large distributed environments. Next, we're going to look at the traditional client-server architecture. It separates the system into two applications where the client makes requests to the server, which then processes them and returns the response. This pattern is fundamental in web applications. Next, we're going to look at peer-to-peer architecture. Now, this distributes tasks or workloads among peers, which are equally privileged participants in the application. It is useful for applications requiring a decentralized and self-organizing network, such as blockchain technologies. Next, we're going to look at hexagonal architecture, also used or called as ports and adapters. This allows an application to be equally driven by users, programs, or automated test scripts, and to be developed and tested in isolation from its eventual runtime devices and databases. Next, we're going to look at CQRS, which is Command Query Responsibility Segregation. It segregates the handling of command input and data retrieval, enabling independent scaling and optimization of each aspect. This pattern is particularly beneficial in complex domains where the read operations outnumber the write operations. And finally, we're going to look at space-based architecture. Now, this addresses issues like concurrency, load balancing, and data consistency by using a space-based pattern, typically involving the use of a tuple space or a shared space to coordinate between different nodes. Now, each architecture style that we are going to define here or go in detail here offers different benefits and trade-offs, often influenced by specific project requirements, scalability needs, the desired flexibility of the application, and other factors such as team expertise and maintenance expectations. We're going to go in details of each and every one of them in this video, and we will look at all the benefits, the architecture, how the data flows, where are its implementations. So stay tuned. Layered and tier architecture. The layered architecture, which is one of the most common software architecture patterns, structures applications into separate layers, each having a specific responsibility. This separation of concerns ensures that each layer is independent and interacts only through defined interfaces. Typically, this architecture includes 3 or more layers. Let's look into details of this. Now, let's say, for example, a user, how would he interact with a layered architecture? The first layer that it interacts with is the presentation layer, which manages user interface and browser communication logic. Next is the business logic layer, handles data validation, business rules, and task performance. Then we have the data access layer, which manages data persistence and storage. And finally, the database layer stores data in a relational or NoSQL database systems. Now, some of the benefits of this layered n-tier architecture is maintainability. It changes in one layer generally do not affect other layers. It's also development simplicity, where developers can focus on one layer at a time using standard programming paradigms. Reusability. Layers are designed to be reusable across different applications with similar architecture. Testability. Independent testing of each layer is possible due to the separation of concerns. What are some of the drawbacks? Now, first one is performance overhead. The additional abstraction can introduce latency, particularly if many layers are involved. There's complexity in deployment. Managing and deploying changes across layers can be complicated, especially in large applications. Rigidity. Heavy interlayer dependencies can make it difficult to modify the architecture without affecting multiple layers. Let's look at an example. Now, consider an e commerce application structured into a layered architecture. So, in this particular same, we have our different layers. Now, for the presentation layer in an e commerce application, a web interface where users browse products, add items to their cart, and place orders. The business logic layer will be the core computations like applying discounts, calculating taxes, and managing stock levels. The data access layer will be communication with the database to fetch, store, and update product or user information. And the database layer contains the SQL or NoSQL database systems where all the data is stored. Now let's look at another real world analogy. A restaurant operates similarly to a layered architecture. So for example, for the presentation layer, the front of the house, which is the presentation layer in this case, where interactions with customer occurs. The business logic is the kitchen, where meals are prepared according to the menu rules. The storage room is the data access layer, where ingredients are stored and managed. And the suppliers is the database layer who provides the ingredients. Now let's look at some of the popular use cases. We have enterprise applications. Now many enterprise level applications are built with layered architecture due to the need for strict separation between data management and user interface logic. We have financial systems like banking and financial systems often use layered architecture to segregate the processing of transactions from customer facing elements. Now, this architecture is especially prevalent in applications where business rules change frequently, but the interface or data storage patterns remain relatively stable, allowing for easier updates and maintenance. So that's all for the layered architecture. If you have any questions, please leave me comments. Event-driven architecture, EDA. Event-driven architecture is a design paradigm centered on the processing and handling of events. In this context, an event is defined as a significant change in state or an occurrence recognized by software which can be processed by one or more software components. EDA is highly responsive, making it suitable for environments where stimuli from different sources are asynchronously handled. Now, what are the different components of EDA? First one, we have the event producers. Entities that generate events. They do not know what will happen once an event is produced. Next, we have event consumers, which are entities that react to events. They listen for specific types of events to which they are designed to respond. Next, we have the event channel, the medium through which events are delivered from producers to consumers. And then we have the event processing, which are techniques for responding to events, which can be simple reactions, complex decision making processes, or event transformation. Now, what are the benefits and drawbacks? One of the benefits is scalability. The architecture allows for easy scaling as components can be added or removed without impacting other parts of the system. We have flexibility. New event types and event consumer logic can be added with minimal impact on existing components. Responsiveness. Systems are highly responsive to changes or user actions as they happen in real time. Asynchronous. Components operate independently and do not block each other, which is efficient for resources. Now, drawbacks. First one is complexity in tracking. Debugging can be difficult because the flow of processes is not linear. Dependency on messaging. The architecture heavily relies on the integrity and reliability of the event messaging system. Inconsistency risks. Ensuring data consistency across services can be challenging, especially in large distributed systems. Now, let's look at an example. Consider an online shopping platform that uses event driven architecture. For the event producer, we have the shopping cart service, which emits an event when a user adds an item to their cart. Now, the event channel, in this case, the event is published to a message broker. Then we have event consumers. Multiple services listen to the cart update event. The inventory service checks if items are in stock. The pricing service calculates the total cost. The recommendation service updates the user recommendations. Then for event processing, each service processes the event independently and takes appropriate actions like updating databases, sending notifications, or adjusting user interfaces. If you have to look at the real world analogy, a home security system acts much like an event driven architecture, where we have sensors, which are event producers, detect movements or door window openings. The security system, which is the event channel, receives these signals. We have alarms and notifications, which are event consumers, which are triggered in response to these detections. Now, some of the popular use cases for this architecture are real-time user interfaces, where applications where the user interface must update in real time as data changes, such as in dashboards or live monitoring systems. We have IoT systems, where managing and reacting to a large stream of data from IoT devices. We have complex event processing, where applications in finance, security, or logistics that require immediate response to complex scenarios based on event patterns. Now, event driven architecture is particularly advantageous in systems where it is expected to handle a large influx of events with minimal latency, thereby providing an interactive and dynamic user experience. If you have any questions, please leave them in the comments. Thank you. Microservices architecture. The microservice architecture structures an application as a collection of small autonomous services, each implementing a specific business capability or function. These services are independently deployable, scalable, and communicate with each other using lightweight protocols, typically HTTP or messaging queues. This architecture style is particularly favored in environments that demand agility, scalability, and a high degree of flexibility. Now, some of the components of microservices architecture includes first individual services. Now, each service is a mini application with its own business logic and database capable of being deployed independently. Then we have the API gateway. Acts as a single entry point for all client requests, routing them to the appropriate microservice. Then we have the service registry, service discovery, or service registry, mechanisms for services to find and communicate with each other, often implemented using this service registry. Then we have the distributed messaging. Communication between services is handled asynchronously, typically through a message broker. And then we have the continuous delivery integration, which is CD or CI. Automation tools are crucial for testing, deploying, and scaling microservices independently. That's done through this. Now, if you look at through the entire picture, the clients, which are the web, mobile, and other platforms, are your client applications. Now, there is microservices, which consists of all these different things that we just spoke about, the components of microservices. The web, mobile, and other applications access these microservices directly through the API gateway, and API gateway routes them through the services which the user called, and that goes through the distributing messaging, which is the message broker. So, this is the entire architecture for a microservices architecture. Now, what are the benefits and drawbacks? First is scalability. Each service can be scaled independently, allowing for efficient use of resources based on demand for specific function of an application. With flexibility, new business functionality can be quickly developed and deployed without affecting existing services. We have resilience. If one microservice fails, it does not bring down the entire system. We have technological diversity. Teams can choose different technologies and programming languages best suited for their services specific needs. Drawbacks: complexity. Managing many services and their interactions can become complex. Data consistency. Ensuring data consistency and integrity across services can be challenging due to each service managing its own database. Network latency. Increased communication between services over the network can introduce latency. Operational overhead requires robust operational infrastructure to monitor, log, and troubleshoot a distributed system. Let's look at an example. Here we have an e-commerce application built using microservices, which might include the following services. Now, if you look at in the services section, we have provided first one is the user service, which manages user registration, authentication, and profiles. We have product service, which handles product inventory, descriptions, and pricing. Then we have the order service, which manages the shopping cart, order processing, and status tracking. We have payment service, which handles payment processing, including credit card transaction and invoices. We can have other services like, for example, recommendation service, which generates personalized product recommendation based on user behavior. Now, each of these services would operate independently, have its own database, and communicate with others as needed using the RESTful APIs or messaging queues. Now, let's look at some real world analogy. Now, think of a restaurant franchise chain where each branch or service operates independently but adheres to common standards and interfaces. Each branch manages its inventory, orders, and sales, but they communicate and synchronize with the headquarters and other branches for broader business functions. Some of the popular use cases include a large enterprise applications. Large organizations use microservices to enhance agility and manage complex applications across diverse departments and teams. We have e-commerce platforms, ideal for handling the varying loads and functionalities required by modern e-commerce sites. Then we have the streaming services. Services like Netflix and Spotify use microservices to handle distinct functions like user subscriptions, content streaming, and user recommendation efficiently. Microservices architecture offers a robust methodology for developing large scale complex applications where each component is maintained by different teams and where flexibility and scalability are paramount. I hope you understood Microsoft services pretty well here. If you still have questions, please leave them in the comments. Monolithic architecture. Monolithic architecture is a traditional model for designing software applications. In this architecture style, all components of the software are integrated and tightly coupled within a single program from a single platform. This includes the application's user interface, business logic, and data access code. Monolithic applications are simple to develop, test, deploy, and scale horizontally by running multiple instances across different servers. Now, if you want to look at monolithic architecture in a diagrammatic fashion, let's say we have our web, mobile, and other platforms. Now, what are the different components of monolithic architecture? First is the user interface, the part of the application that interacts with the user. Then we have the business logic, which contains all the rules and algorithms necessary for processing the data of the application. We have data layer, manages data and database interactions. Next, we have application integration, which integrates with other systems through APIs or messaging systems as part of the single application stack. This is the entire structure of a monolithic architecture system. Very simple and straightforward. Now, what are the benefits? Simplicity in development and deployment. Easy to develop, test, deploy, and scale because everything is unified. Performance can offer better performance because all operations are tightly integrated and in process. Troubleshooting easier to debug and monitor due to a singular nature. Drawbacks scalability issues. Scaling requires scaling the entire application rather than parts of it that needs more resources. Limited flexibility. Updating or modifying the application can be cumbersome as changes in one module might affect others. Long term maintenance. As the application grows, its code base can become large and complex, making it difficult to maintain and update. Let's look at an example where we consider a banking application built as a monolithic architecture. So, for the user interface, the web pages or the mobile app screens through which user interact with their accounts. For the business logic, we have the code that calculates interest, validates transactions, manages user data, etc. For data layer, we have database operations for storing and retrieving account details, transaction logs, etc. For application integration, we have communication with external systems like credit scoring services or government financial APIs. If the bank wants to update just the way interest is calculated, the entire application might need to be redeployed, not just the interest calculation module. Let's look at a real world analogy. Monolithic architecture is like a single engine airplane where all components, engine, wings, fuel, system, are integral. If the engine needs an upgrade, it impacts the entire airplane operation. Some of the popular use cases include small to medium web applications, good for applications with well defined boundaries that won't require frequent scaling or updates. We have simple CRUD applications where applications primarily performing create, read, update, and delete, which is CRUD, operations on a database benefit from a monolithic approach due to the simplicity and lower operational overhead. Monolithic architectures are well suited for projects with a limited scope, smaller teams, or when rapid prototyping is needed. They also for they allow for straightforward development and deployment process but may pose challenges as applications grow in complexity or when more flexibility is required for independent scaling and updating of different parts of the application. That covers our monolithic application. If you have any questions, please leave in the comments. Service oriented architecture SOA. Service oriented architecture is a design pattern where the application consists of multiple services that communicate over a network to provide a set of capabilities. This architecture allows for services to be reused across the entire organization, reducing redundancy and increasing efficiency. SOA focuses on enhancing the ability of applications to interact seamlessly across different platforms and networks. Let's look at what different components of SOA or SOA are. First, we have services, which are modular units of software that perform a specific business task and can be reused by different systems within an organization. Next, we have a contract or an interface which defines how services interact through a formal definition which includes messages, operations, binding information, and the protocol. Next, we have the service repository, a central directory where services are published and can be found by consumers. And last, we have the service bus, which manages communication and data exchange between services through a reliable and secure platform. All these different, the entire SOA architecture or the system can be accessed through the service bus where the web, mobile, and other platforms can actually interface with the service bus to reach to the right services that it needs. Now, some of the benefits of SOA or SOA are reusability. Services are designed to be reused reducing the effort and cost of the software development across the organization. Agility: changes to services can be made with minimal impact on the consumers of those services. Interoperability: designed to work over different platforms and technologies, facilitating interaction between disparate systems. Then we have scalability. Services can be scaled independently, allowing the system to handle increased load by scaling only the necessary components. The drawbacks include complexity. Managing interactions and integrations between services can become complex. Performance overhead: the additional layers of communication can introduce latency and reduce performance. We have dependency management, where changes in service implementation must maintain contract integrity to avoid impacting service consumers. Now let's look at an example of an airline reservation system using SOA might consist of several distinct services. We have the flight scheduling services, which manages flight times, gates, and availability. We have booking service, which handles reservations, ticketing, and customer data. We have customer relationship management with CRM service, which manages customer profiles, frequent flyer programs, and service preferences. We also have payment services, which processes payments and interacts with banking services. Now, each of these services communicates over like has a contract, has service repository, and the service bus using standardized message formats and protocols, allowing them to be maintained independently by different teams and accessed by web, mobile, or other platforms. Let's look at a real world analogy. A city's public transport system can be thought of as an SOA service where buses, trains, and trams provide transportation services using a common set of rules and interfaces, which are timetables, ticketing systems, and operate independently but cooperatively to serve the city's transportational needs. Now, some of the popular use cases for this architecture is enterprise applications, where large organizations use SOA for integrating heterogeneous systems and promoting reuse of existing IT investments. We have government services, where SOA facilitates the integration of different government services and provides a framework for agencies to collaborate effectively. We have healthcare systems, which integrates diverse systems across hospitals, clinics, and other healthcare providers to ensure seamless data flow and improve patient care outcomes. SOA is particularly beneficial in complex business environments where systems need to be highly interoperable and adaptable. This architecture enables organizations to build robust systems that can evolve easily and integrate across different platforms and technologies. That's it for SOA architecture. If you have any questions, please leave them in the comments. Client server architecture. Client server architecture is widely used software architecture pattern in which client applications request resources and services stored on a server. This model divides the workload between the providers of a resource or service known as servers and the requesters known as clients. Clients initiate communication sessions with servers which await incoming requests. Now, what are different components of a client server architecture? The first is the client. The client is the front end application that users interact with. It sends the request to the server and displays the response it receives. Clients can be desktop applications, mobile apps, or web browsers. Next, server. The server is the backend system that provides resources, data, and services. Servers can handle client requests by performing the required operations and then sending the results back to the client. Next, network. The communication infrastructure that allows clients and servers to exchange information, typically over the internet or an intranet. Now, what are the benefits of a client server architecture? First, centralized management. Since resources and data management are centralized on the servers, it simplifies administration and updates. Scalability. It's easier to scale the backend independently of the client, handling more requests by upgrading server capabilities or adding more servers. Efficiency. Resources are utilized only when necessary, and the distribution of tasks can be managed dynamically based on demand. Security. Centralized control over data and resources enhances the security measures as they are implemented on the server side. Let's move to the drawbacks. First, network dependency. The performance largely depends on the network. Poor network connection can lead to delays or failures in client server communication. If server overload, the server can become a bottleneck if too many clients send requests simultaneously. And then we have maintenance cost. High quality servers and their maintenance can be costly. Upgrading and securing servers also add to the expense. Let's look at an example of an online banking application. Now, in this particular case, we have the client, which is a user's browser or mobile banking app that sends requests to check balances, make transfers, and pay bills. The server is the banking system's server processes these. The banking system's server processes these requests, performs transactions, updates accounts, and sends back confirmation details. Then we have the network, which is the internet, which facilitates the communication between the banking app and the banking servers. Let's look at a real world analogy with the restaurants. A restaurant operates in a client server model where diners, which are the clients, request meals and the kitchen, which is the server, prepares and provides the meals. The waiter or waitress acts as the communication link, which is the network between the diners and the kitchen. Some of the popular use cases for this particular architecture is web applications, websites where the client, the browser, interacts with the server, hosting the website content and functionality. We have email systems where clients, which are the email apps, connect to a server to send, receive, and store emails. We have database applications where client access a database server to query, update, and manage data. Now, the client server architecture is foundational for many types of applications, especially those involving a clear distinction between user interface and data processing. It provides a robust framework for building scalable, manageable, and efficient software systems suitable for environments ranging from small scale applications to enterprise level solutions. If you have any questions on client server architecture, please leave them in the comments. Peer to peer architecture, P2P. Peer to peer architecture is a decentralized network architecture where each participant or peer acts as both a client and a server. This model allows peers to share resources such as files, bandwidth, and processing power directly with each other without requiring a central coordination point. P2P networks are highly scalable and robust as they can continue to operate even if some peers disconnect. Now, some of the components of P2P architecture include first peers, which are nodes in the network that both use and provide resources. Each peer is an autonomous entity that directly interacts with other peers. We have shared resources, data or services that are available to other peers in the network, such as files, content streams, or computational resources. We have an overlay network, a virtual network layer that sits on top of the physical network, connecting peers in ways that optimize data sharing paths. Then we have routing mechanisms, protocols and algorithms used to discover and connect to other peers, handle resource requests, and manage data transmission paths. This is an overall gist of peer to peer architecture. Now, what are the benefits? First one is redundancy and reliability. Data can be stored on multiple peers, increasing the robustness and fault tolerance of the network. Scalability: as more peers join the network, the total system capacity increases, often improving performance and resource availability. Cost efficiency. The distribution of resources, provision, and consumption can reduce the need for expensive server infrastructure and bandwidth. For drawbacks, we have security risks. The decentralized nature can make P2P networks susceptible to security issues such as data integrity attacks and the spread of malicious files. Then we have data consistency. Ensuring that all copies of shared data are up to date can be challenging. Dependency on peer contribution. The performance and health of the network depend on the contribution of resources by all peers. Free riding peers consuming resources without providing them can degrade network performance. Let's look at an example. A well-known example of P2P network is the BitTorrent protocol for file sharing. In this, the peers are the individual users' computers that download and upload files. We have the shared resources, which are files that are segmented and shared across multiple peers. We have the overlay network, which is the BitTorrent protocol. The BitTorrent protocol creates a network where peers connect directly to exchange pieces or files. We have routing mechanisms. BitTorrent clients use information from torrent trackers or distributed hash tables to find out other peers who have the file pieces they need. Let's look at a real world analogy. Now, a neighborhood tool sharing program can serve as an analogy for a P2P network. Each household, which is peer, can borrow tools, which are resources, from others and lend out their own tools without a centralized lending library. The efficiency and variety of tools available increases as more households participate. Now, what are the popular use cases where this architecture is used? First one is file sharing applications. Services like BitTorrent allow users to share and download large files efficiently by distributing the file transfer load across many peers. We have cryptocurrencies. Blockchain technologies such as Bitcoin use a P2P network to manage and verify transactions without a certain authority. We have distributed computing projects. We have initiatives like SETI at home use volunteer computing power from peers around the world to process data for scientific research. P2P architecture leverages the power of network collaboration to achieve scalable and efficient resource sharing. It's particularly effective in scenarios where central coordination is not desirable or feasible, making it popular choice for file sharing, distributed applications, and collaborative networks. If you have any more questions on P2P, leave them in the comment. Hexagonal architecture, also known as ports and adapters architecture, was designed by Alistair Cockburn. It focuses on the decoupling of the application's core logic from external factors such as databases, user interfaces, and other services. This architecture emphasizes the separation of concerns by isolating the application's domain logic, the part that encodes business rules, from its interactions with the surrounding environment. Now, some of the components of hexagonal architecture include first, the domain model, central to the application, containing the business logic and data it represents, the state and behavior of the business scenarios. Ports, interfaces that define the points of interaction between the application and the outside world. There are two types of ports: primary, driving ports. These are used by the outside world to send commands to the application. Example, a REST API. Then there is secondary, driven ports. These are used by application to communicate with external systems or services. Example, a database. Next is the adapters. Now, implementations that connect the ports to the actual external technologies or services. They translate between the format and protocols used by the external resources and the domain model. We have the primary adapters, which handle input into the application. Example, web controllers. And then we have the secondary adapters, which handle output from the application to the external systems, example database repositories. This is the entire architecture for an hexagonal architecture or ports and adapter architecture. Now, what are the benefits? Benefits include flexibility and maintainability. By decoupling the core logic from external components, the application becomes easier to maintain and evolve. Interchangeability of components. Adapters can be easily swapped out for alternative implementations without affecting the core domain logic. We have isolation of the domain logic. Simplifies testing and development as the business logic can be tested independently of the external elements. There comes the drawbacks, complexity. The architecture can be overkill for simple applications where such a high degree of decoupling is not necessary. The learning curve, developers might find the architecture challenging to understand and implement correctly, particularly if they are not familiar with its principles. Let's look at an example. Imagine a web application for booking flights, which has the domain model, which contains classes and methods that model flights, reservations, and customer interactions. We have primary port, which is a REST API through which users interact with the application to search for flights and book them. We have secondary port, which interfaces for accessing a database to store and retrieve booking and user details. We have primary adapters, a web controller that processes HTTP requests from users and invokes the appropriate domain services. And then we have the secondary adapter, a database repository implementation that handles all database operations required by the domain services. Now let's look at a real world analogy. Think of hexagonal architecture like a universal power adapter that allows an electronic device, let's say the domain model, to be charged from different types of power outlets, which are the external systems, around the world without needing to change the internal components of the device. The popular use cases include enterprise applications, where business logic needs to remain stable while technologies around it evolve. We have financial systems, where the core processing must remain isolated from external interfaces like banking networks and payment gateways. We have e-commerce platforms, managing core functionality such as order processing independently from user interfaces and payment systems. Hexagonal architecture is particularly useful in complex applications where the business rules are stable and longevity is desired. But external interfaces may change due to technology shifts or new integrations. This architecture style ensures that the application's core logic remains untouched by changes in the external layers, facilitating easier updates and adaptations. If you have any questions on hexagonal architecture, please leave me in the comments. Command Query Responsibility Segregation (CQRS) is an architectural pattern that separates the operations that modify data, which are the commands, from the operations that retrieve data, which are the queries. This separation allows each to be optimized independently, improving performance, scalability, and maintainability. CQRS is often used in conjunction with event sourcing, where changes to the state of an application are stored as sequence of events. Let's look at the components of Command Query Responsibility Segregation (CQRS). The first one is the command model, or also called as the write model, which handles create, update, and delete operations. It is responsible for processing commands, validating them, and applying changes to the data. The next one is the query model, or also called as the read model, optimized for read operations. It provides multiple views of the data that are tailored to different client needs. Next, we have the command handlers, components that handle command logic, typically by validating commands and then applying them to the right model. Then we have the event store. In systems using event sourcing, the event store captures all changes as events, which can then be replayed to restore or reconstruct the state of the right model. We also have the query handlers, components that handle data retrieval requests from the read model. Let's look at the benefits of CQRS. First is scalability. By separating read and write workloads, each can be scaled independently according to demand. We have optimized performance. Read and write data models can be optimized for their respective operations, improving overall system performance. We have improved security. Command and query operations can be secured differently according to their specific needs. And finally, we have flexibility. New read models can be added without impacting the write model, making it easier to evolve the application over time. Now, for drawbacks, first one is complexity. Introducing CQRS can add complexity to the system, especially in terms of deployment and maintenance. Your data synchronization, by keeping the write and read models synchronized, particularly in high volume environments, can be challenging. And finally, we have consistency. Immediate consistency is not guaranteed unless additional mechanisms are implemented, which can complicate the architecture further. Let's look at an example where you consider an e-commerce platform implementing CQRS. Now, the command model manages all updates related to user information, order placements, and inventory updates. We have the query model, which provides various views for different users, such as personalized product recommendations, order histories, and real-time inventory levels. And then we have the command handlers, which will validate and execute operations like placing an order, which involves checking product availability and processing payments. We then have the event store, which stores all events resulting from commands such as order placed and inventory adjusted. And finally, we have the query handlers, which retrieve data from displaying product details, user profiles, or order statuses based on the optimized query model. If you want to look at a real world analogy of this, we can think of CQRS can be likened to a restaurant kitchen, which is the command model, and its dining area, which is the query model. The kitchen handles the preparation and cooking of meals based on orders, which are the commands, while the dining area is set up to provide guests with a pleasant dining experience, which are the queries. Both areas function independently but serve the common goal of a well operated restaurant. Let's look at some of the popular use cases. First, financial systems, where transaction integrity write and reporting read requirements are significantly different. We have the e-commerce applications, separate management of customer orders, which are write heavy operations, and product browsing, which is read heavy operations. We have gaming platforms, managing game state updates, which are the commands, and providing game statistics to leaderboard, which are the queries. CQRS is a powerful pattern when there are clear distinctions between how data is modified and how it is read, allowing each side to be tuned and scaled to best serve its purpose. It's particularly useful in scenarios where performance, scalability, and responsiveness are critical. If you have any questions, please leave them in the comments. Space-based architecture (SBA) is a distributed architecture pattern designed to avoid traditional scalability bottlenecks associated with high traffic, data intensive applications. This architecture is named for its use of space, a middleware component that serves as a combination of the combination of the process's memory, message queue, and database. It supports distributed data grids and parallel processing to manage the load by eliminating the reliance on a single point of failure and contention points. Components of space-based architecture include processing units, independent runtime containers that host the application components, managing both processing logic and data storage. We have spaces, which are in-memory data grids that distribute and synchronize data across the network. Spaces act as a shared memory environment for all processing units. We have load balancer, distributes requests and computational load evenly across the processing units. And finally, we have the persistent storage. While the primary focus is on in-memory data management, persistent storage is used for data durability and recovery. What are the benefits of this particular architecture? Scalability. Easily scales out by adding more nodes to the distributed grid. It has performance set. High performance due to data being held in memory and reduced data access latency. We have resilience. Fault tolerance as the architecture avoids single points of failure, data and processing can be redundantly spread across multiple nodes. Drawbacks include complexity. Managing and configuring a space-based architecture can be complex due to its distributed nature. The cost. High memory usage might lead to increased cost, especially when scaling out involves adding more hardware. And we have overhead. Synchronization and consistency mechanism across nodes can introduce overhead and affect performance. Let's look at an example for real-world financial trading platform using space-based architecture could look like this. First, processing units handles different aspects of the trading process such as order matching, risk management, and transaction processing. Then the spaces store current trading positions, pending orders, and recent market data distributed across all nodes to facilitate quick access and updates. We have the load balancer, which distributes incoming trade requests and queries to the nodes based on their current load and data locality. Then we have the persistent storage, which is used for achieving used for archiving completed transaction and logs for compliance and auditing. Let's look at a real world analogy. Consider a space based architecture like an air traffic control system where multiple controllers, which are the processing units, handle different sectors of airspace, which are spaces. Each controller has access to real time data with flights and weather and communicates with other controllers to manage air traffic smoothly and safely, with redundancy to ensure no single point of failure. Popular use cases for this is real-time data processing, applications such as stock trading platforms, and online gaming where latency can significantly impact performance. We have highly concurrent applications, e-commerce sites during peak times like Black Friday sales. We have large-scale cloud services, services that require high availability and rapid scalability, such as media streaming and large-scale web applications. Space-based Space-based architecture provides a robust solution for applications requiring high availability, scalability, and performance. It is especially suitable for scenarios where application demand is unpredictable and traditional scaling methods, scaling up or out via additional relational database resources, are insufficient or cost prohibitive. If you have any questions on any of the sections that we have covered here or any of the architectures we have completed, leave them in the comments.